Alright, we're going to talk today about a couple more properties of gases. So the first one is partial pressures. So Dalton's law of partial pressures says if you have a mixture of gases inside of a container, there's going to be a total pressure inside of that container. So we could stick a barometer on that, measure the pressure inside, and the total pressure is going to be equal to the individual pressures of the different gases added together. So if we've got like a mixture of carbon dioxide and oxygen, if we take the individual carbon dioxide and the oxygen separate, they would have their own pressures. And then if we combine them together, the total pressure in the container would just be pressure of carbon dioxide plus the pressure of oxygen. So here's an example of a problem. We have 100.8 grams of oxygen, 289.8 grams of nitrogen inside of a scuba tank, and it's a 6-liter scuba tank. We want to know the partial pressure of each of those gases and then the total pressure inside the tank. Now, we're not given any pressures here. We're only given grams. Can we convert grams into pressure? Yeah, this will be a perv nerd problem then. Don't waste a lot of time going through the calculations in this slide. I'm assuming you know how to convert grams to moles and then use perv nerd. So we convert the grams of nitrogen, find out we have 10.34 moles of nitrogen and 3.15 moles of oxygen. And then in our perv nerd equation, we're just going to rearrange it to solve for pressure. And once we have that, we can just plug in the different moles. R, T, and V are going to be the same for both. It's going to be 20 degrees Celsius, so 293 Kelvin, and 6 liters. And so when we plug that in, we find out that we have 41.5 atmospheres of nitrogen and 12.6 atmospheres of oxygen. And then the total pressure, according to Dalton's law, would just be the pressure of nitrogen plus the pressure of oxygen, which means it's 54.1 atmospheres total. So we've heard the term partial pressures before because we use it during equilibrium. When we've got gases and we refer to them in atmospheres, we use the partial pressures to indicate each of them. So in the case of partial pressures, then it's like concentration of gases. So here's a ice table that we're going to set up. So if we've got some knuckle and it's in a sealed container, when it reaches equilibrium, the pressure of nitrogen is nitrous oxide is 0.458. We want to find the pressure of Cl2. And so initially then in this sample, there's not going to be any of those two. We don't know what this is, so we won't know what that is all the way through. Over on this side, though, this is going to increase by 2x. This is going to increase by x. So then in equilibrium, we would have these values right there we can plug in, so 0.458. And we would be left with x of Cl2. So we're trying to find out what Cl2 is. And hey, look, so this is 2x, and that's x. And so that means this value right here would just be half of that one because x is half of 2x. So 0.458 divided by 2 means that we would have a pressure of Cl2 equal to 0.229 atmospheres. So we didn't do too much with mole fractions during the solutions unit, although we did talk about it. It plays a much bigger role with gases because mole fractions and partial pressures are actually directly related. So once again, a mole fraction is just the moles of one component in the mixture divided by the sum of the total moles of the components in the mixture. So here's an example. We've got several different components, helium, argon, and chlorine gas inside of a container. We're going to find the mole fraction of each of those. I won't go through and do each of them. We'll just find the mole fraction of one of these. If you want some practice, you can do the other three on your own. And so we would get the number of moles probably using perv nerd, but in the case of the mole fraction of helium, so x of helium, it would be equal to the moles of helium, which is 6.70 moles, divided by the total number of moles. So that's going to be 6.7 plus 2.5 plus 1.6. And we do not multiply this by 100. It's not a percentage, it's a fraction. And so we would get 0.620 as the fraction inside of the container that is helium. So this one's already worked out for us, but it's a good concept to understand. So when we're dealing with mole fractions, so the total is always going to be equal to 1. So the fraction that is helium plus the fraction that is hydrogen plus the fraction that is neon in the case, of this sample. Let's change it like this. Okay, so those three would add together to be 1. Just like if they were percentages, they would add together to be 100%. So knowing that, then, if we have two of the fractions, so we know the neon and the hydrogen are 0.233 and 4.78 respectively, we can solve for the fraction that is helium by subtracting those two from 1. And that tells us the fraction of helium is 0.289. Alright, so tying it together then, we can relate the mole fractions to the partial pressures by multiplying them. So the partial pressure of a particular gas is equal to its mole fraction times the total pressure. So let's say we have a container at 0.97 atmospheres, and we find that the mole fraction of oxygen is 0.210. What's the partial pressure exerted by oxygen? So the pressure of oxygen would be equal to its mole fraction, so that's 0.210, times the total pressure. And so 0.210 times 0.97 is going to be 0.20. And so that means there would be 0.20 atmospheres would be the partial pressure of oxygen.